All right, we'll leave a little early, okay? I'll give you that much at least. Oh, sorry, Phil. All right, guys, does everybody have all my people that survived yesterday? Does everybody have this handout here?
Yes.
Yes, everybody? Okay. So what I want to do, I got some more of these, yes. First thing I want to do is on this sheet. I'm pretty sure we finished this sheet, but I have a request from somebody to talk about midpoints. So maybe just copy this down in your notes. Make this a little picture, and we'll do the same problem again with midpoints this time. Just gonna show you how they work. So we talk about left endpoints, we talk about right endpoints. That's weird, man. Huh? Okay. So, we talked about left endpoints, right endpoints. Why would you sometimes want to do both? Take the average, because one of them or the other one might be under or over.
Yeah.
That makes sense. We just try to imperfectly fill in a curved space with these straight edge shapes, these rectangles. Yes? Okay. Like it. Welcome, Lloyd. Try to find a seat. I gotta laugh instead of cry. So we did this already. We did left endpoints, we did right endpoints, we averaged them, and I eventually showed you how to do it in the calculator, yes? So I'll show you that again for anybody that missed out. But remind me, so this is the same problem, but now I want to do midpoints. That would be M, that's crazy. The work is exactly the same. How do I figure out how wide my rectangle is going to be? I want to go from 1 to 4, and I want to use 6 rectangles. So what's my width going to be? Yeah, 4 minus 1 divided by 6, so 1/2. How do I figure out where my first rectangle sits? Like, where's its base? I've got to start where? No, I've got to start where? What number?
1.
1. That's what it tells me. I got to start at 1. And then, of course, where's my first rectangle end?
1.5.
1.5. You guys all with me? So I can find my first rectangle 1 to 1.5. That's its base, right? What's going to determine the height?
The
Midpoint. And what is the midpoint of 1 and 1.5? Yeah, 1.25, yes? Okay. So 1.25, the middle. So that's going to determine what the height of my first rectangle is. And that's going to what determines the height of every rectangle. Now here's what's really nice. How wide did we say each rectangle is?
1/2.
Half. The minute I know the first midpoint, where's the next midpoint going to be? How wide is every rectangle?
1.5.
So if I know the first midpoint, the next midpoint is
1 over.
1/2 up, and then 1/2 up. I need that to make sense. So the left endpoint of one rectangle is half away from the left endpoint of the next. The right endpoint is half away from the next, so the midpoint is half away from the next, because they're all a half wide.
So the midpoint is like a more accurate way of...
If I draw some more in, what's happening with the midpoints that we had to kind of like, where would my next midpoint be, first off? I'm at 1.25 right now. 1.75. So like right here maybe. And where's my next rectangle gonna end?
At 2.
Yeah, this one ended at 1.5, so this is gonna go to 2, I like it. This one's gonna go from 2 to 2.5, and my height's gonna be based on 2.25. So do you see how, real quick, each rectangle is kind of averaging itself out, yes? So a midpoint kind of has the left and right averaging happening all at once. Does that make any sense? I love it. Some of you guys, I love it. You have this look on your face, but you're saying yes, but you're going. Yeah. Do you all agree? So if I would have had, if I did this with left endpoints, then my rectangle, my first rectangle would have looked like this. Much shorter, yes? If I did it with right endpoints, my first rectangle would have looked like that. Much taller than this one, yes? So midpoints kind of average both of those out for us. You guys see that? It does make the computations a little bit grosser, because normally you get some kind of worse decimals, because you're going to be in between numbers, but we're in freaking calculus. That kind of shit doesn't bother us. Talk for yourself. So here, I can keep doing the visual, but how do I set this up? Do you guys remember what I can always do with this? Because the way we do it, it's always the same number. I can factor it out, because I just got the big E just means add up a bunch of shit, and they each have delta X in it, so I can factor that out. So that's my 1/2. And then I'm gonna have F of 1.25.
1.25.
And how do I continue? Just keep adding 0.5. And how do I know when to stop?
When you get 6 of them.
Yes, exactly. So 1, 2, 3, 4, 5, 6. And 3.75 makes sense, because my last rectangle should go from 3.5 to 4. So 3.5 would be the midpoint of that. Are you guys, do you see that?
Yeah.
So it's kind of a trade-off. Instead of doing left and right and then averaging, I could do mid, which requires a little more internal work, but then I'm there. I've kind of got the average sort of done at the same time. So there are a couple homework problems I want you to use midpoint. I highly recommend what you do is you find the base of a rectangle and then just go to the halfway point. And then from there you can just keep adding the width. It's crazy. Maybe. And now you just plug and chug, right? You can make the table and the calculator like we did before. You guys kind of with me? Do you guys, anybody still have this? What did we get?
Oh,
Don't have my-
11.875.
Yeah, that's what we got after averaging. Yes?
Yes.
I like it. So very quickly. Yes, I like it. Thanks, Dave.
Realized you were back there.
Better late than
You
never.
scared me at first.
So just bear with me for a second, very quickly. If I put this in, and then I go to my table, let me set my table, yes. And then I put in here, oh shit,
Really? You're gonna put that in your calculator?
yes. 1.25, 1.75, 2.25, 3.25, 3.75, bam! Holy shit, does that look right? Okay. You can almost see that. So now, if I add those up, let me see. Gotta look over there so I can actually see them. 1.9375. This is terribly exciting. Everybody just.
3.4375.
Thank you so much.
4.4375. 4.9375. 4.9375. And 4.4375.
Okay, good lord. Thank you, sir. She's like, this man's struggling. You help him. So I'm gonna do 1/2 times Jeff and a half. all this stuff, yes? I just want to just kind of quickly, 1.9375 plus, can you read your own writing? 3.4375 plus 4.4375 plus 4.9375 plus 4.9375. There's the turn of the parabola. And plus 4.4375. You get 12.06. So it's just slightly over. But do you agree with me that's closer to the right answer? Like David said, it's 12. 12 is the right answer. This is, sorry, I'm way zoomed in. Okay. This is what we got when we averaged left and right endpoints. And this is still 12 and a half away. Do you guys see that? 0.125. If we do midpoints, I got 12.0625, which is only 6 off versus about 12 off. Yes? So the midpoint kind of averages itself as it goes. So it's got a little give and take. The middle of the work is worse, the end of the work is better. Maybe, maybe. So the whole idea of what we're doing right now is using approximating shapes to get weird areas. So I want to use the easiest freaking shape in the universe, because the whole problem here is I don't know the area of the damn dome. Are you kidding me? But I know the area of a rectangle. That kicks ass. And just to let you know, in calculus 2, you could use trapezoids instead of rectangles. And you're all like, do you want me to take calc 2, or are you trying to talk me out of it? It sounds horrible. You're not going to do it all the damn time. It's just really briefly. Because you could use different shapes. We just picked a rectangle because those are nice, but you could use a trapezoid. And wouldn't a trapezoid have a better chance to fit because it has one side that's diagonal? Do you guys understand what I'm saying? So you can improve on this approximation technique. But we know better. We know the ultimate improvement. How do I really improve the hell out of this? How do I, by hand, get the exact answer? What's the immediate thing we can do to make our approximation better?
More squares.
More rectangles.
Or rectangles.
Yes? More rectangles. And so what's the ultimate way to make it the absolute best? Use how many rectangles?
Infinite.
Use an infinite number of rectangles, Jeff, of course. Because we're crazy people and we know limits. So that's why we're able to do that shit. Can you draw infinite rectangles?
No,
Don't try it, kids, okay?
I don't want to.
No, I don't want to either. That would be your inheritance. You inherit from me drawing these damn
I
rectangles.
get really good at drawing rectangles.
Yes.
So, yeah.
Okay. Rectangles of infinitesimal width. That'll be a problem. So let me do this. Before I get into this technical thing, I was gonna call it hell, but
Well,
I love it, but you guys can feel how you want to. I want to do a very specific thing. So you guys can handle me for a second. Can you handle me? Can you guys please graph that for me? What shape will it have? Yeah, absolute value looks like this. There's a negative in front, so it's going to look like
Down the
this. It's shifted to the...
left.
left. It's shifted up.
Up.
Right?
Sure, it's shifted up 2, and it's shifted right 3.
To right three.
Very quickly. Do you guys remember talking about transformations of functions?
Yeah.
That's a freaking -3, Jeff. Why the shit are you saying it goes right 3? Because this is me going into the absolute vodka bar, yes? And that's the shirt I have, absolute vodka. The word vodka inside of absolute vodka.
That's funny.
And what happens right before I get in the damn bar is somebody takes $3 away from me. If it's a $10 cover charge, how much money better do I have to bring to make sure I get in?
13.
$3 more. So I have to overcome the fact that it's going to take 3 away from any input. So all of my inputs have to be 3 bigger than they used to be. That's why if it's inside with the X, it does the opposite of what it looks like. Sure. David's like, Jeff, they made this thing called a graphing calculator. Shit. So this shifts over 3. and up 2. And it's reflected. So just to kind of graph this a little bit quickly, are you guys, it's got a slope of 1. Is that okay? Do you guys see it's got a slope of 1? If I were to graph this, what does it look like? 0, 0, 1, sure, be more specific. 1, 1, negative 1, 1. What is this slope?
1.
It's got a freaking slope of 1. This slope is negative 1 because the absolute value forces it to turn, yes? But it still has a slope of 1 or negative 1. Are you with me? So this also has a slope of 1, correct? It's just been translated over. Move up 2, and I'm going to go down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. There, that's a much quicker way to do that silly shit. This is basically a line that's been forced to go against its will. It still essentially has a slope of 1. Are we suddenly going to do a lot of graphs of absolute values? No, you're just doing this right now. What does this mean?
Integration from
So again,
like the integration from 5 to 1.
1 to 5, but be. What does that mean? We don't know that yet. We don't know that yet. Yes?
The difference of x from 1 to 5.
No. No. Okay, so remind me. This was the height of a rectangle, and this was the width of a rectangle, and then we add them up from 1 to n, however many rectangles, correct? How did we boost the resolution of that? How did we make this better? We let the number of rectangles go to
infinity.
This becomes elongated S, dude. Yes? Infinite sum, we just took the letter S and we elongated it. I did tell you about that last time, yes? Pretty sure I did. Like some of you guys are emphatically saying no, and some of you guys are emphatically saying yes. So I'm going to say that's a wash. Okay. So this symbol came from elongated S for infinite sum. When I let the rectangles go to infinity, what happens to their width? And I know I talked about this, so I definitely talked about this. Yeah, it goes from delta x to become how small? Infinitesimally small. So it goes from delta x to dx. And then this, I need you to understand. The example we just did. Do I use, how many inputs did I use? That sounds weird.
6.
How many inputs? 6, because I had 6 rectangles, yes? How many inputs will I use for this?
Infinite.
Infinite! Do I leave any x values out?
Nope.
Nope! Every single x value from a to b gets used. So therefore, this just becomes the whole frickin' function, because it uses every... Do you guys see how there's a one-to-one correspondence? This shit means the same thing as this. This is just cleaner. You guys agree with me this is cleaner?
Yes.
Okay. So this means, how do I interpret this statement right now? What's the area under the function from 1 to 5? Now look at this problem. Look at your graph. Look at my graph. Look at the wall. No, look at the graph. 1 to 5. Yes? Can anyone please figure out a way to answer my question without doing any frickin' rectangles and get the exact answer? 1.5 base times height. If the shape I am looking at is a shape I know the formula for, I'm going to use the frickin' formula. Screw it. There will be some problems in the homework that are just making sure you understand this is all about area. If I got a curvy dude, oh shit, I've got to use some rectangles, help me out. I don't know curvy dude formula. If I got a freaking triangle, if I got a circle, I don't need help. I can just do that shit. I'm gonna give the exact answer without using infinite rectangles. Thank you very much. Yes? So what would this area be? What's the height?
2.
2. And what's the base?
Five.
So what's 1/2 the height times the base? 5. So this area is 5. I don't need freaking rectangles, Jeff. Screw you. Okay. So again, if the shape I'm looking at is a shape I have a formula for, use the formula, right? If the shape I have is a shape I have no formula for, it's curvy. We don't have a lot of shape, unless it's a circle, we don't have a lot of things for curvy to use. Then I'm gonna have to use rectangles to approximate it, yes? You guys kind of with me? So you're gonna see both of those kind of problems. There's not a ton of this kind of problem, because that's just to really emphasize we're talking about areas, and if I can get the area quickly, do it. But if I have this kind of problem, moving over to this handout, yes? If I have this kind of problem, Lloyd, what's up? Sorry. Where am I at? Sorry? Oh, the base is 4, yeah. Yeah, so the area should be 4. Thank you. This one. Now look at this. Is kind of cool. This is kind of cool. I wanted to point this out last time, and I forgot all about it. Where am I going from to?
From 0 to 3.
So let's kind of make this a better visual for ourselves and say 0 to 3, yes?
Mm-hmm.
Just for a second. Can you estimate the area just by counting certain things? Can you see what I'm saying?
Yeah.
Didn't I give you something
I don't
with a
want
grid
to.
so you can see how many square units there are? Now, you don't have a perfect thing, but can you estimate? Don't say anything. Estimate how many little squares there are. Don't say anything. I know they look like they're all rectangles because my scale is different, but they're squares. How many whole squares are there? 14. Yeah. 14, yes, I agree. There's 14 whole squares. Plus, if you put these together, don't you get at least a whole square? Yes?
Mm-hmm.
So let's say the answer is at least
16.2.
16. We got 14 whole squares, and then 1, 2, slightly more than whole squares. You guys kind of with me? Again, the thing we just did just happens to be because the graph I was given has a grid. I already know the answer should be a little more than 16. You guys with me? Will you always be able to do what I just did?
Nope.
No. Will you always want to do what I just did?
No.
Okay. But in this example, it's really easy. I can just see it. So I already know it's got to be around 16, probably a little bigger than 16. So, can you guys try to do number 1? And I know I keep using these upside down parabolas. It's just they're just nice to use. But my poor little dude got little measles or something. So you're using what kind of endpoints?
Left.
Left endpoints. I like it. Oh, yeah. Did I turn that video on?
Yeah.
Okay. This morning I had half the lecture that didn't record us again. What's the very first thing you want to calculate?
The delta.
Delta x, the width, 11. And how do you always get that?
3 minus 0.
Yeah, how far you want to go on the x-axis? In this case, 3 minus 0.
Over 4.
And how many steps you're going to take? 4 steps. I like it. 3/4. This is where you all go. Why can't you just make it 1 for one step? Too bad. Too damn bad. Yes. I'm sorry? Oh, you need this? Okay. Did you have the other one? You had this one, right? I'll give it to you. Does everybody else have this guy? You need one? Okay. I love you guys. You're just sitting there going, well, FML. Everybody else good? So here's a good way to do this. Sort of like what I did earlier with the midpoints. Where's the first rectangle start?
At 0.
0. And where's it end?
3
3/4.
fourths.
0.75. About right there, yes?
0.75.
Which side of this is going to determine my height? The left end point. So I'm going to go use the left side, I'm going to go up, and then over, and then down. Oh shit, I went too far. What's the next step take me to? 3/4 plus 3/4 is 6/4 is
3/2.
3/2, which is 1.5. So again, I'm going from this to this. Left end point tells me how tall my rectangle is going to be. You guys see that? Your picture is not going to affect your work, except if you have it mislabeled or something. So if you don't draw the right height, it's not necessarily going to throw your work off, but part of what I'm going to grade is, can you draw this thing correctly? Where am I going to stop next? 2.25. And my left end point is going to determine how tall that is. And I got 1, 2, 3 rectangles so far. I don't want to use 4, so my next one should be my last one. So I'm going to end at 3, and my left side is going to determine how tall that is. You guys? So figure out the width on the x-axis, and then go to the left side if it's left end point, or go to the right side if it's right, and just draw until you hit the function, over, down. Okay.
Say that one more time.
Figure out the width. Figure out the base of your rectangle. If it's left end point, go to the left and draw up until you hit the function, over, down. If it's right end point, go to the right, go up, hit your function, go over, down. I mean, that's it. All right, finish it up. Oh, pulled out nice. Go. 26. Still have 38 people here supposedly. So what I always do when I'm doing this concrete, finite number of rectangles, put the width, and then just start. What's the first height? F of
0.
0. And that's 1, 2, 3, 4. So just always make sure everything's jiving, right? Make sure you end up with 4 expressions, because you're supposed to have 4 rectangles, all that kind of stuff. And now it's just a bunch of plug and chug, right? So you can use your table if you want to make it quicker. F of 0 is nice. F of 3/4 I want some help with. Don't make me do it. 6875? F of 1.5, 8.5 minus 2.25 is 6.2. He said with such confidence. And then this should be 5.6875. Look at me go! Math boy knows math. Right to the papers. Okay. And then I just blah 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 blah. Yes? Let's see. 1.3. What are you trying to do yourself, Jeff? 7.5. 625. I don't know. Is that right? What is it? Jesus Christ. Oh, I forgot to do 3/4. I haven't done 3/4 yet. Okay. That's overall. I'm with you. I'm with you. Let me see how close I got. 4 plus Jeff. 5.168. So 5 times 2 plus 6.25. Go to, what did I do? Oh, I put a parenthesis. Yeah, look at that. Sorry. I just got the right answer. And then times 3 divided by 4, so times 3/4. 16.21875. Does that jive with what our estimate was? Yeah, we said a little over 16. Yeah, that's kind of nice. That feels kind of nice. We did a lot of work and we got kind of like where we were before. That also feels kind of bad. You're like, why did I do all that work? I already knew the answer. In this case, we did. We won't always have that. Now we're gonna do this really weird ass shit, okay? And I kind of told you, it's going to be a truncated version of earlier this semester. Before we learned derivative rules, what did I have to do to figure out the derivative? Limit definition of derivative. We lived in that for a little while, yes? Would you guys agree we lived in that for a little while? This is going to be very quick. We're going to live in it like we're here and then we're going to continue. Yeah, so it's a very truncated version, but I need you to see where this stuff comes from. That could be just. So on this paper, the other side of this paper, it's got the steps that you want to use. We're going to do all the same steps we just did. It's just that we're doing it with unknowns. So it looks worse, but it's the same. The weirdest part of this whole thing, and I'm not going to make you memorize these. I'm going to give you these. This one should just be understood. If you add up 7 to itself 5 times, what do you get? Don't do it, just do it. I mean, don't add. What do? 7 times 5. That's all this thing says. If you add up a constant n times, you get n times c, c times n. That's all that says. So you don't need to memorize it because you already know it. These are not nearly as obvious. Last time we did prove this one though, yes? Okay. We talked about the urban legend and it was a very interesting one. You don't want to make a movie out of it, but it's still kind of neat. Okay. 50-50, the first 100 numbers, crazy. So try to follow the steps. I'll put the steps here so you can kind of, you don't have to keep flipping back and forth. Do the first couple of steps and then I'll catch up to you.
So do we just keep n and we don't know yet? Or
Yeah, we don't know n. And we're letting it go to infinity. So instead of 4 rectangles, we're using n rectangles.
Okay, so Jx will be b by 0.
Yes, totally. And b and a we know.
Yeah.
We're still going from 0 to 3?
Yes.
Yeah. So do the first 2 steps, and then I'll catch up to you. You got the example there too? Right, you can do the example if you want to. We put this over here actually. Oh, still part stuff. Just to remind you guys, once we figured out delta x up here, what was it I immediately did with it? No, but when I went to draw the picture, right? That was the next step I did. Once I figured out 3/4, I started at 0 and I added, holy shit. And then I added another 3/4. So I added 2 3/4 and so forth. That's all this thing is saying is start at the beginning, that's crazy, and add this many steps. That's all that says. So again, the math we're doing is the same. It looks worse because there's less numbers.
Is there an infinity?
Huh?
Is there an infinity or was there
N is N. Yep. Because I used 4 rectangles. How many could I have used? 6? I could use 7. I could use 11. I could use 121. So I'm just saying N for anything you want to use. What are you guys getting for the width?
3/4.
Yeah, 3 over N.
3/4.
So what are you guys getting for X? What's A? 0 plus 3I over N. Is that cool? So you get 3I over N. And what is 3I over N again? It is XI, yes? XI is 3I over N, yes? So how do I rewrite F of XI? F of 3I over N. Which is? This is just a function. Functions, there's no thought. You just throw shit in, yes? So what's F of 3I over N? 4 plus
6.
3 times 3I over N minus 3I over N squared. See, I mean, function notation can never be difficult, ever. Just whatever's in it, you put it in there. Ooh. I know, it's weird. It's weird. The shit we're plugging in is weird. Who cares? Just plug it in. Right now, I don't care. Can I clean that up a little bit? Okay. And you're all like, we know you don't care, Jeff. Oh man, come on. So F of XI is 4 plus
3 over. Oh, 9. 9 I over.
yep, minus
9.
9I squared over squared. Three squared is 9, I squared is I squared, N squared
Oh,
is N
okay.
squared. And one little thing, just think, I don't know if I should even say this. This I is not complex number I, okay? Yes, yes, yes. I almost didn't want to say that because somebody out there was like, I wasn't even thinking that, now I am. Shit. This is its own thing. This is just the index. This is just like variable I.
Why is the 9 still squared at the very end?
Well, because what is N squared? What is N squared? N squared. What is I squared? I squared. And what is 3 squared? 9. So of course everything's squared in that because what's being squared here? Everything. Yeah, cool. Okay. So now I've got this.
Multiply it by.
Now I just throw stuff in there, yeah? So the limit as n goes to infinity, sum I equals 1 to n, f of xi, which is this business, yes? What's the one last piece?
3 over n.
Yeah, delta x, which is 3 over n. Stop for a minute. All that's inside of there. I can make that really clear, okay? Let's see if you guys remember. Physically, what does this represent?
The f of x or the x.
Physically, in the graph.
The function.
For a rectangle, that represents the height. Physically, what does this represent?
The width.
The width. So I'm still adding a bunch of rectangular areas, yes? I've just more explicitly put what every height is, and then more explicitly put what every width is. What's the last thing I worry about in this whole thing I'm working on right now? And you're all like, the whole damn thing, no. What's the last thing I'm gonna do?
The limit?
The limit, yeah, so just let him come for the ride. He's just out there having a good old time, just waiting his turn. Okay. Maybe. Does this look funky?
Yes.
Is it surprising
No.
that doing something involving an unknown number of rectangles will end up with a funky looking? Of course not. It's not surprising at all. Of course it's going to be a little funky. Is it difficult? What do you think we're going to do next?
Take the 3n out.
Opposite. No. Why?
Distributed.
I could take it out. It would make a future step a little bit more difficult. And of course, the not enough room kid is struck again. Let's see. So you guys can just continue in the notes. I'm sorry. So what I'm going to do, I need you to see, eventually I want to break these sums up into separate parts. And if I bring the 3 over n in right now, that step is going to be easier to manage. To be really honest, the math doesn't matter, but I'm just going to do it this way. So if I bring that in, I get 12 over n plus 27i over squared minus 27i squared over n cubed. And again, every step I'm taking is basically the same as this. Okay. Now what I'm gonna do, I'm gonna split up each sum. I'll make this a minus, it's my fault. Okay, let me make sure this is understood. You guys kinda with me? Let me do a little, don't even write this down. I wanna make sure everybody really understands what I just did. If I had to do 4 plus 5 plus 6 plus 2 plus 5 plus 8, isn't that the same thing as 4 plus 2 plus 5 plus 5 plus 6 plus 8?
Yeah.
Okay, so I can split up a sum of sums in almost any way I want to. So I'm going to add up these terms first, add those to the sum of these terms, subtract the sum of those terms. I'm going to get the mathematically, math doesn't give a shit, it's like whatever you want to do, human. I can add anything in any order I want. So I can split those sums up. Yes, sir?
Does that really do anything for us?
Oh, hell yeah. I appreciate the question, Tyler. Tyler's like, oh, good job, Jeff, you rearranged things. Well, you didn't say that, but I picked up on that. Okay. What that does for me is, didn't I give you a rule for the sum of I?
Yeah.
Do you guys see how one of these, I could uncover a sum of I? It's good I get some shit out of the way, something that somebody wanted me to do earlier, but I'm gonna do it now.
Take out the.
Yeah, so let me see. According to each sum, what's the variable?
I.
I. So what can I take out of this?
Everything that is
Everything.
I.
What's left inside?
1.
Do I have a rule for this?
Yes.
Yes, I do. Okay. Plus, what can come out of this guy?
The 27n squared.
27 over n squared. Why can it come out? Because it doesn't have an I. And it doesn't even see what's going on. So then I equals 1 to n. A math dad joke, I don't give a shit. This is really, really, really crazy important. The sum sees I as the variable. Every other damn thing in there is a constant according to it. When we had n was 4 for the rectangles, n was a constant, correct? So n is a constant. It's just I'm not telling you how many rectangles yet. Haha. So I can take that shit out. Minus 27 over n cubed sum of I squared. Now, What is the sum from 1 to n of 1? If I add 1 up
N.
n times, what do I get?
N.
That's insane. But true. And what do I replace the sum of I with? And I'm not going to make you memorize that, I'll give it to you, but what do I replace it with?
N times n plus 1 over 2.
Kick ass.
Yeah.
Minus, and what do I replace the sum of I squared with? Something even weirder. I don't know if I can remember it. I'm going to look at it. There it is.
N times n plus 1 times 2n plus 1 over 6.
And I'll put this out there again. I said this the other day, but if anybody wants to see the proof of this, I can post it up on campus. Just gotta remind you. If you're like, I'm fine, Jeff, then don't tell me. What's 12 over n times n? 12. And what's the limit of 12? 12, okay. Plus. What's the limit? Let me see if you guys are cool with this. Do I have to rewrite this shit, please? What's the degree of the top here? N squared. And what's the degree of the bottom?
Squared.
Squared. So what's the limit as n goes to infinity?
1.
1 over 1. So what am I left with in this term then?
27
27
over 2.
2. The limit of
Which
this
is not it.
is 1 because the degrees are the same. And the limit of the degrees to being the same is the ratio of the coefficients. Yes, you learned that back in pre-calc. We talked about it again this semester. And you're like, that's not enough, Jeff. Bullshit. Now this one, sorry, let me do the limit. Be really, really careful here. I'm trying to save you some time so you don't have to multiply that shit out. What's the degree of the top? Cubed. If I did multiply out and the largest degree I'd get is cubed. Is everybody with me? What would the number be in front of it though? 2. So 2n cubed. And the bottom is n cubed. You're
That would
left
be
with 2.
2 over 1.
Yeah, like the n cubes cancel in a way. The same degree. It's the coefficients directly, so it'll be 2 over 1. So minus 27 times 2 over 6. Yes? So I get 12 plus 13 and a half minus 9. Yes? Yes, 27 times 2. Yes, because this limit was 2. Yes. And so I get 3 plus 13.5 is 16.5. That is the correct answer. How close did we get with our Fisher Price 4 freaking rectangles? Pretty freaking close, yeah? Why? Why is that not surprising? It's a well-behaved function. It doesn't go insane. You know, like it's fine. I do enough of that myself for everybody. Real quick, just to show everybody. Does somebody remember, how do I do this in my calculator?
Do
What was the
you
problem? It's over here, John.
well, you put the thing, you put the,
Thing in the thing.
yes.
Can you be less specific? So 4 plus 3x minus x squared. And then I cast the right spell, the incantation for the magic to happen. What is that? What do I? Second.
Second.
This, so Lingardium, calculus, and then down there, it looks good, right? Look above that, again, D1DS. It's gonna graph it, and I have to tell it. Of course I gotta
The
tell it,
lower
because it's
than
dumb.
what's-
I wanna go from
You want to go from 0
0?
to 3.
to 3. What does it say? 16.5! Alright, I need you to understand what just happened. We humans, by hand, just did something that they hardwired into this crazy ass expensive thing. We just did that by hand. You understand? We got 16.5. Like, alright, good for us. Okay. I love you guys. Okay. By the way, while we're here, what is this? This is 4 here, right? What would happen if I integrated from 4 to 5? What should be true about my answer?
That it should be 3/4.
If I go from 4 to 5, No, there is. If I go from 4 to 5,
Going to
the
be-
area is gonna be
Oh, over it.
negative. So let's see, if I go from 4 to 5,
Oh.
negative area. Some of my colleagues don't like talking about negative area, but in this case, this is not necessarily a physical area. This function, if it represents the rate of change of profit, during that time period, we lost money. It's negative. It's flowing away. So all the negative sign really indicates is a loss versus a gain. You with me? It doesn't mean physically a negative area. That's some shit I don't want to get close to, because I don't know what's going to happen. Yes? That's the shed people made in algebra. Negative 10 feet by negative 12 feet. I'm like, I'm not coming to your shed, man. Okay. So down here, this is something I did before, and I'm doing it again. Little teaser. Can you guys take a moment and calculate what we affectionately call big ass F for this guy? Don't say anything. Try to calculate the antiderivative, big ass F. Huh? Oh, okay.
Got it.
And then do what I asked, the f of 3 minus f of 0. What are you guys getting for big ass F?
4x plus x to the fourth minus 1/3.
Careful,
x to
careful,
the
careful.
fourth plus-
Okay. Guys, this is beautiful. This is perfect. What's the derivative of x to the fourth? 4x cubed. The functional piece is what matters. Constants do not matter. We just need to make them work. They come for the ride. When I take derivatives, don't constants just come for the ride?
Mhm.
Same thing with integration. Where did x come from? What would I take a derivative of to get x?
X squared.
X squared, except 2 would come down. There's no 2, so I have to have x squared over 2. What's the rule? Integral of x to the n. Antiderivative of x to the n. X to the n plus 1 divided by plus c. Okay. So the integral of 3x, the 3 just comes for the ride. Just write him, he's just there. He's just like, I'm just here. The integral of x, new power would be 1 plus 1, divide by the new power. Yes? It's not a mixed number, by the way. Okay. So what happens with x squared? X to the third
1
divided by 3,
1/3.
yes? So I get 4x plus 3 halves x squared minus 1/3 x cubed. And my request to you is what's f of 3 minus f of 0? Oh, by the way, plus c, yes? So somebody help me out. What is f of, big ass f of 3?
16.5.
Yeah, that'll be 12 plus, that's really close, by the way, you're not quite right. 27 halves, yes? Does this look familiar, by the way? Minus 1/3 of 27 is 9. Plus c. Minus, what is big ass f of 0?
C.
C. C's cancel, and I get frickin' 16.5, yes? I've done this twice now. And I've told you we are going to make a connection between antiderivatives and integrals. At the moment, what does it mean when I say integral? The only thing that means at the moment is what? When I say integral. The integral sign? Finding the what under what?
The area under the curve.
Oh, sorry. I was something like I said that. Right now, that's all an integral means. There's no way in hell it's like obvious that it's connected to the antiderivative. Why would those be connected? So that's the next thing I want to work on is connecting those two things. Yeah. And then that'll be enough for today, okay? We're gonna do that. Now don't get too excited because it's gonna take a little while, so. But I told you I was gonna let us out early. We all deserve that for whatever reason. You can either go celebrate or I don't wanna know if you're gonna celebrate, I'm gonna drown myself. Meet for a future, okay. I'll be here. No.
So the voting, we can vote in 5 minutes.
Huh? No, no, it's
Was it, at the end of it, was it negative 9 plus C? Or was it more C?
And the C's got canceled.
C's got canceled, and I just had 12 plus 27 and a half minus 9. The C's canceled here, right?
How do you get a minus?
Huh?
How do you get, oh, it's because it's
Minus
minus.
1/3, 3 cubed, yeah. Okay. So guys, we're about to do, and again, don't get too excited, it's gonna take a little while. I'm gonna define a function in a way that you've never seen it before. You know, like, what do you do? So I'm gonna define a function in a very kind of freaky way. So far, what we've done is I've got an f of x, I've got an a, I got a b, blah, 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 blah. This would be the integral from a to b, f of x dx, yes?
Yes.
Because the x-axis, the y-axis is amazing. That's the basic definition of that symbol. It's the area under the curve. Why does it look the way it does? Elongated S, yes, because it's an infinite sum, so we're just like, a lot of us mathematicians were a little bit inebriated or whatever in the day, so that's how, let's just make an S really long. So we're like, sounds good. I'm gonna create a function that utilizes this. So let me kind of preface this a little bit. So I can be given this whatever function doing whatever the hell it wants to, yes? Couldn't somebody say, I want to know the area from A to something? And then somebody else could come along and say, well, I want to know from A to something else. Well, I want to know from A to something else. So I would need to make a function where the input tells me where to stop. This is different. So I want to make a function where I always start from A. But my input, if I put a 3 in, I'm going to go from A to 3. If I put a 4 in, I'm going to go to A from 4. So the answer is going to be the area under the curve from A to whatever I put in. Very often we call this, you're not going to believe this, we call it the area function. Okay. Let me see if you guys, I cannot, what does X represent? In this what I've done so far, what does X represent? The endpoint. Very specifically, the endpoint somebody wants, yes? So can I still call this the x-axis?
Mm-hmm.
No, I cannot. Because x
Oh,
means a
right.
single thing now, yes? This is the trippiest part of this. All right, let me make sure you guys, so the beginning of this should make sense. I want to integrate. I want to get the area from what to what? A to X. So is this cool so far? That should be the only place X shows up, because that's all it does. All it does is say, stop here. So I can't put f of x inside, because that would be specifically f of 7, or whatever somebody wants x to be. It wouldn't be the function, would it? I don't know if you guys are really with me. Isn't x, can't we choose what x is? Can't you choose x to be 11? So if I put f of x inside, that would be f of 11. That wouldn't give me the area, it would just be a constant inside. I wouldn't get the area under the function, it would just be a number inside now. So what I gotta do then, what we do normally when we have this situation is we use the letter t to represent our axis. We are using x already. So inside I'm gonna put f of t dt. And real quick, x don't mean shit. There's a really interesting history about why we use x. But did we have to use x? Yeah, we could have y equals mw plus b. We could have used w and y. Why not? That means, yeah, I agree. It's got issues, but it's, you know, it's first name of my first level last name. So I'm looking at it. Yes.
So we did that because X is just a point.
Yeah, I can't, yeah. Do you all agree that the T inside of F has to represent everything that could be from A to X? It's gotta represent everything. X specifically represents one thing. When I call this the x-axis, is any point on there X? No, every point on there is X.
Yeah.
Yes? So I can't call it the x-axis. I'm saying this one point is X, so no. Okay. So just to show you an earlier example, remember we just had this situation a second ago? Yes? Make this big, boom, and I'm just gonna. I could tack on there like, starting at 6 it goes. Okay. So let me ask you a question. If this is f of t, and I define g of x to be the integral from 1 to x, f of t dt. Okay, stop for a minute. When you signed up for calculus, did you ever think there'd be a day you'd see this image? No. What is g of 5?
Area under the curve from 1 to 5.
Yeah, which is what?
4.
4. We did that earlier, right? So this would be the integral from 1 to 5 of f of t dt, which is 4. What is g of 6? Careful, what's the g function always go from? 1 to whatever I plug in. So what's the area? From 1 to 5 is 4. Does 5 to 6 add any area? Nope. So this is still 4. So what about g of 7?
You're not subtracting the negative area for that?
Oh, this specifically is just this piece. Sorry. That's a good question. So I just want the absolute value part. So what I've drawn is what f of t is. I like it. So what's g of 7? So I'm starting from 1 and I'm going up to 7. So what's this area?
4.
And what area am I adding? 2. So I get 6. So there's going to be at least one problem, if not one more than that. I think there's 2 problems kind of related. One is very specifically this. And then the other one's a little bit more amorphous, but the same idea. So if the shape I'm looking at is a shape I know the geometric area of formula 4, do that, because that's all this wants, is the area, right? So this is very funky. You have never seen a function quite like that, where the x is stuck in this thing, and the freaking integral symbol's pretty new to us too, so the whole damn thing is new, Jeff, why not? All right, maybe. So, yes, go ahead.
So what you drew was just a function next to the...
Yeah, this is f of t. This whole thing, I should put f of t here. This is f of t. Yeah, so like Lucas was saying, if I took this and I had this piece of this here, how would I do? So if I put that there, you guys with me? So this is now a different picture. Can somebody help me figure out what g of 6 would be? This much is how much? 4, Jeff. Dear God, we've already done. I know. Be quiet. How do I figure out this much?
Minus 1.
Yeah, it'd be
Because that's
1/2
its height is.
times 1 times 1, yes? And it's negative, so it'll be minus 1/2. So what is g of 6 then? 3.5, yeah. 4 minus 1/2, yes? This kind of canceled out part of this. Okay, maybe. So this would be like we're making profit and then we lost some profit at the end. Yes? Yes?
So if that's a given function, that would be, like, would they call it, like, let's say they said f of x equals, then they gave us some polynomial, that's not related to f of t, we can't use that.
Oh, no, so, I just have to use a different variable. That's all. It's just, if I said f of x is x squared, would it freak you out if I said f of w is w squared? Does that freak you out? I'm just using a different letter. In that case, I'm just using it just because I feel like it. In this case, I have to, because x already has a job. You can't do two things at once.
So you still draw f of x.
Yeah.
For f of
It's just would have a t instead of x. It doesn't actually change anything mathematically. I just can't. It's sort of like the biggest mistake students make on a problem, like a word problem, and they say you have this box, right? And they go, well, I don't know this, and I don't know this, and I don't know this. Okay, what mistake might they have made there? They have assumed what?
That they're all
They
the same
assume that they're
size.
all the same length. So if x has a job already, maybe the base is square, that's cool. It can't also be there. Because then that's implying something's not true. So x already has a job. It tells me where to stop. It cannot also represent every value in here. So I gotta bring in some little dude to help me out. And I don't blame you, this is weird. But I want you to realize it doesn't change anything mathematically. It's still the same stupid function. So what is this? This function is really just giving us the shape in which we're going to calculate areas based on where somebody wants me to stop. Now, last thing for today. Oh, look at that. Well, this is going to take a while. Okay.
Oh boy.
We're still going to leave it. Don't worry. It's not as early as you might want. Okay. Now the question becomes, and now we're sort of getting into 5.3. In 5.3, just to let you know, you can immediately see it. 5.3 is called the fundamental theorem of calculus. And there's a part 1 and there's a part 2. So I affectionately call that FTOC. Instead of calling it the fundamental theorem of calculus every time. So when I say use FTOC1, that means use the fundamental theorem of calculus. Okay. So there's two parts to this. And how important do you think this is? Oh my God. Right. This is the underpinning for every damn thing, basically, for in mathematics from here on out. So it's a little important, so I don't feel any pressure. Okay. So what I want to do, so now we've got this idea of this function set up. So now my question, now listen, what have we done this entire semester? Once we learned derivatives and we got to chapter 3, we would say, oh yeah, we know this function, so what is its derivative? Oh yeah, we know this function, so what is its derivative?
Mm-hmm.
Oh yeah, we know this function, so
Now we get to
what
learn
is
the
its
rules.
derivative? Yes, and you're like, oh, thank God this derivative is gonna be really, really nice. It's gonna take a little while to get there. Okay, so everybody kind of with me? Every function we know, as a calculus student, you should be curious, what the hell is this function's derivative? I wanna know. Yes? And we know a lot of them, we don't know all of them. This function we just made, this is the first time we've ever seen it, and we immediately go, well, what's this derivative? So let's investigate this thing's derivative. So let me draw the situation. This is f of t, this is t. Okay. So how do we investigate derivatives?
Limit.
The derivative is the rate of change of output over a given change of input, yes?
Mm-hmm.
And normally we let that change go to 0, right? I'm sorry. So what I'm gonna do is I'm gonna step plus h out. That's what we did before, yeah? X plus h. So I'm gonna step here, x plus h. It's too big of a step. Let me make this. I really want, so I'm gonna be right here, yes? Right there, x plus h, because h is gonna get really tiny, yes? Whatever area this is currently, so my question really is, if I change my input a little bit, what happens to my output? That's basically what a derivative does for us. So if I step a little bit up, x plus h, how much does my output change? Does anybody see, couldn't I draw this little dude here? Isn't the area of this representative of how much my area has changed now that I've stepped out a little bit further? You guys with me? What is that area? So let me zoom in on this. Let me zoom in on this. How wide is this? H. Because this is x plus h, it's hy. How tall is it? Let's do left side. How tall is the left side? Careful. F of x. Yes? X is here, yes? X is here. So that's f of x, yes? And why do I do that side? Because what am I going to do with h? You all know what I'm going to do with h. I'm going to let it go to. So aren't I approaching that side anyway? So doesn't it only this side that matters? Because you could argue that, I don't know what this thing does, man. You drew it straight, but who knows if it goes, it looks like it's going up. You cheater, you cheating math boy. But it doesn't matter, because I'm going to let h go to 0. I'm going to go back to this wall anyway, yes? Stop for a minute. I really want this to make sense. This is fundamentally what we do with derivatives. How much does it change given a slight change in input? So that's what I'm doing visually. Now I'm going to let that slight change become an infinitesimally small change, yes? So let me see. Yes, okay. G of x plus h minus g of x. G of x plus h. That's the area here, yes? Because g is the area function, yes? What is g of x plus h minus g of x? No.
G of x.
Don't just start telling me, hey!
Or
Squiggly line.
G of h.
All right, you guys see that area there? What is that? Is that g of x?
That's f of
This
t.
area here. No. What is the area? What function gives me the area under f?
Oh, the
G of x does.
X.
So what is this area here up to there? G of
G of
x.
x.
What is the area up to x plus h?
G of x plus h.
How much bigger is g of x plus h exactly?
G of h.
You could do it. What is the area of this sliver?
F
That's
of
what I've
x
written. That's
times
what I've written.
h.
I want to know what it is. Do you all
F,
agree with me?
F of
that-
x plus h,
Listen,
or
listen.
f of x times
What
h?
do I add to g of x to get g of x plus h? Don't I add this piece?
Yes.
How big is that piece?
H times
F of
H
x
times f of
times
x.
h.
We-
Oh my gosh.
That was a trip.
Okay.
No, I don't blame you guys. Don't get me wrong. I'm sorry. There's a lot kind of going on here. We just introduced the g function earlier, dear God, Jeff. Leave us alone. Okay, I'm sorry. But does everybody see it now? That little sliver is what I add on if I go out to x plus h. So this equals h times f of x. Because that's the area of the piece that I added. Can you guys see one step and we get g prime almost kind of showing up? What's the definition of g prime of x? Limit definition. The limit as h goes to 0 of
Oh my god.
g of x plus h
G of x.
minus g of x all over h. You guys see how? Divided by h. By the way, this is approximately. Why is it approximately? Because if h is big, I don't know what that side is shaped, so it's approximate. So I still have to take a limit. So the limit as h goes to 0 of g of x plus h minus g of x over h equals f of x. And you're all like, great, Jeff.
Yay.
You just wrote a whole bunch of shit. Good for you. Good job, Jeff. What does all that mean, dear God, Jeff?
It's the
We just
derivative.
proved. What is this side? What's a better symbol for this side? G prime,
G
yes?
prime, yeah.
That is the definition of G prime of X. We got it in a really weird way. We never looked at it. Why does it make sense? This function's weird, right? So everybody leave us alone. This is weird. Over here, Jeff. Good job. G prime of X equals f of X. So let me go back. Doesn't that look pretty? That's awesome. What the shit does it mean? Okay. If I am given this function, its derivative is just f evaluated at x. Now, let me stop for a minute. I'm of two minds right now, but I immediately want to do FTOC2 because that's the thing that's going to dominate our life, and then I'll show you. So this is FTOC1. What did FTOC stand for again?
Fundamental theorem of
Oh,
calculus.
yeah, that's right.
No.
That's exactly right.
Alright.
Help me out, guys. What is the antiderivative of G
Oh,
prime
God.
of X? No, don't.
G of X.
G of X. What is the antiderivative of f of X?
Big F.
Big ass f of X. I just took an antiderivative, so I better put
Let's see.
let's see. So what we just, I need you to see this. What was G of X again?
The
The
area
interval, right?
of, yeah.
So we just showed, and again, what does this represent physically? And you just said it to me. An area. What is this? The antiderivative of the function that's in there, yes? So this is the connection between the area under a function f and the antiderivative of f. They're actually essentially equal. We got a little bit of cleaning up to do, but basically that's where we are. Okay, we'll let you think about that for a moment. Okay, so I'm gonna come back to this in a minute. Just want to put that down there for right now. Let's think about this FTOC1 business. So let me give you a more specific example. Let's say that I have g of x is the integral from 2 to x of sine of t dt. Understandably, students do this wrong, and I don't blame you. But I want to know what g prime of x is. Yeah, cool. All right, so here's the rule. What's the rule? If I'm given this, g prime is just the function evaluated at the endpoint.
Yeah.
So what's this?
Sine of x.
Sine x. Done.
Yeah.
That's the rule. Isn't that the rule? That's the rule. That's how it works. Now, again, what did we just figure out? The integral is equal to the antiderivative. So of course the derivative of an integral is equal to the stupid original function. Of course it is. It undoes it. Taking the derivative basically kills this because they're opposites. We now know that this symbol is directly related to the antiderivative. So of course taking the derivative of the antiderivative undoes it. Do you see how this function didn't change? What it's evaluated at changes, but it didn't change. So what about this? What if I gave you h of x equals the integral from negative 110 to x
Okay.
of the natural log of the tangent of t squared minus 3t dt.
Oh, okay.
What is the derivative of h? I need more paper. Paper. What's that? Oh, that's funny. Oh, what are you guys done? You should be done.
The natural log of tangent of x squared minus 3x.
Done. Alright, okay. This is basic derivatives. Do we know any rules on top of basic derivatives?
Power rule,
Like
quotient
power
rule,
chain rule,
yeah. Product rule.
Alright, how does this work with chain rule? Let's take a look.
Oh no.
Yeah.
No.
Sorry, I'm a little too excited. So I gave it away. This is going to be chain rule. I want to know why. By the way, do you guys notice how it doesn't matter what the constant is I pick?
Yeah.
We'll see why better in about 10 minutes. 13 minutes. What do you got, Jeff? There. Alright, I'll make this not too bad. So what is, Now I want to know F prime. So why is this chain rule? Is the inside, now this is so weird. Coming back to a normal area function, what's inside the function?
T.
No, here's my function. What's inside of it? X.
Oh.
This is the inside of the function right there. Strange. What's inside this function?
Cosine x.
Chain rule, right? The inside is more than just x. Gotta be chain rule. I love you guys. So what's the rule doesn't change. Like e to the x squared. What's the first step of its derivative? E to the x squared, because the derivative rule for e is itself. And then the chain rule does shit. First step doesn't care. First step is just what's my function. I have an integral function. What's the rule for it? I evaluate the inside thing at, you could do it.
What's inside?
Yes, I evaluate the inside at the end
Cosine x.
times
The inside's term.
the derivative of the inside. There's chain rule. I should really put this out front, but it's okay. I need to.
So
Yes, should be a negative sign. Thank you. Before I kill myself, my poor little.
oh yeah, it's cosine.
Yeah. You guys, that is trippy. Freakiest function you've ever seen in your entire life, I guarantee it. Obviously, it's going to have some kind of freakiness with this derivative. This derivative is actually way nicer than you would think. But it's weird because the inside of the function is like on top of this s. So if that thing is more than just x, that's chain rule. Okay, maybe.
So what if it's just a constant? Or can it ever be a constant?
Like 8 to 9?
Yeah.
What do you guys think?
Yeah.
The
But it
derivative would be
just
zero. Yep. Because then it would be a specific number representing the area. It would be a number, derivative 0. Yeah. Okay. Just like if I said, what's the derivative of cosine of 7?
Whatever the cosine of something.
No, what's
Oh,
the derivative
0.
of cosine of 7?
0.
0. It's just a number. Yeah. So if you plug a constant into a function, you get a constant, so its derivative is 0. Okay. Now, last thing. Sorry. One more last thing. Well, I didn't finish this up yet. No. Okay. So going back to this, let me start here. And just to remind you guys, where did I put it? Yeah. What was g of x again defined to be?
The integral
Yeah.
from a to x of f of x dx.
F of t dt.
Or yeah, f of t dt.
So somebody help me out. What would g of a be? And you have to remember what this represents. What does this symbol represent?
The area,
Area?
inside the curve.
Under f from
A to
a to x. So if I put an a in, that would be the area under the function from a
A to A.
to a. If you go from a to a, what's the area?
Zero.
Zero. It's got no width. So what's g of a? Zero. I like it. I like this fascinating, John. What is g of b? You know, Alan? It would be integral from a to b f of t dt. Yes. Yes. Okay. Sorry. So what would, let's see. Remember this. Remember this. What would f of b minus f of a?
The integral from A to B.
Let's see. What is f of
F
b?
of T.
Wouldn't that be
Oh, that's F of
g of b?
G.
And let me see if you got, well, g of b minus c, is that cool? You guys with me? Do you see what I'm doing? F of b would be g of b minus c. What would f of a be? G of a minus c, is that cool?
Yeah.
Okay. I like it. So what is f of b minus f of a? It would be
G of B
g of b minus c
minus G of A minus.
minus g of a minus c. So what do the minus c's do?
Cancel.
Cancel.
So
You
it'd
get
just
g of
be
b minus g of a. What did we say g of a was?
Zero.
So this is g of b. And what did we say g of b was?
The integral from A to B of f of t dt.
No, again, I swear I can sense from your perspective what this must feel like. Man, he's writing a lot of shit down. Look at all that shit he wrote down. Did you was there any individual thing that didn't make sense? If g of x is a to x, then g of b is a to b. Whoop-de-doo. G of a is 0 because we know it means the area from a to a, that's 0. The big ass f stuff comes directly from the definition from right above. So what I want you to notice is we just showed a shortcut of how to evaluate the integral from a to b. And by the way, let me write down what we just got to. Better hurry up, it's going away. I'm gonna burn it. Build myself a little fire. Okay, so what we just figured out is that the integral from a to b of f of t dt equals f of b, big ass f of b minus big ass f of a. Why are you looking over there, John? All right, let me actually show you what I'm writing. Do you guys, I want you guys to be with me. Why did we have to use t earlier?
X can't do two jobs.
Yes, do I have an x in here anymore?
No.
Can't I bring x back then? X backs? Sure, Jeff. So, not a big deal. I need you to really see that. I can call this the t-axis. I can call this the x-axis. It don't change a damn thing. We call it the happy face axis, and a whole bunch of happy faces everywhere. Yes. How did we just calculate this earlier? Didn't we have this long? Where did I put it? This exciting. Damn it all! I want to flash this up here. There it is. Come here, you. This, yes? Jabba, 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 jabba. Yes? Now, I know you're sad. You're still going to have to do this for the homework.
Ah, crap.
But we just figured out a much quicker way. How does this function relate to this function? This function relate to this function?
It's the
It's the
antiderivative.
antiderivative. So let's see. Look at this one. You ready? This problem here.
Mhm.
And I wanted to know the area from 2 to 5.
Mhm.
What would that look like here?
That would be
Integral?
the integral from
2 to 5?
2 to 5 of the 4x.
4x dx. What is the antiderivative of 4x?
Uh,
2x squared. Now, real quick, I'm not gonna put a plus c because, let me show you. Isn't this big ass f of x?
mhm.
So the next thing I'm gonna wanna do is plug a 5 in and plug a 2 in. Do you guys see that? Plug a 5 in, plug a 2 in and take the difference, yes? Wouldn't both of these have c if I put a plus c? Wouldn't they just cancel? Okay, so I'm not just taking an antiderivative. I am finding what we're calling a definite integral. I'm still finding the area, I'm just using antiderivatives to help me. So here's the notation we use. What do I want to plug into this? From what to what?
F of 2.
From 2 to 5. This is the notation we use to remind us, oh, this is what I want to plug in here. So 2 times 5 squared minus 2 times 2 squared. F of b minus f of a. Two times 25 minus 2 times 4. I get 50 minus 8. Life, the universe, and everything. What was the answer we have? Now look. Look at this word. Look at this word. But versus boop. Yes? Now again, you're gonna have to do this shit because you haven't done section 5.2 yet. When you finish with 5.2, we're gonna do this shit. So it's basically the same thing as limit definition derivative before we learn the shortcuts. You guys kinda with me? So, real quick, I want you to redo this problem. Actually, didn't tell you honestly, we already did. Didn't we figure out big ass F? Didn't we do f of b minus f of a? Okay, so let me make you a fresh problem. A nice fresh problem. I want you to calculate this integral. No, make this 2. Yeah. That's plenty. We'll do that. I'm gonna give you a second one. Haha. Bring this down a little bit. Something I want to point out, this is the funkiest little operation. This is the first time ever we see these two things are the symbol for the function, for the operation. These two things go together. They're like the first ever bookend function notation that we've ever seen. So we literally throw a function in the middle of the two. When I find the antiderivative, these both go away because these both are telling me to find the antiderivative. Do you guys follow? I sometimes get students think that this becomes x. This thing's job at the moment is to tell me what I am integrating with respect to. So what am I considering to be the variable here? X. So if this said dy, I would consider y to be the variable. What is the antiderivative of this? X to the third?
1/3.
Plus?
Negative.
Alright.
No. Nope.
Let's do
one,
minus,
1/3.
and then the power goes,
It goes.
I'm integrating,
To
I'm
1.
anti-differentiating.
It goes to negative
So
1.
the power always goes up.
Oh, yeah.
When I take a derivative, the power goes down.
-1.
So it'll be x to the -1 divided by -1, right?
Mm-hmm.
Now I kind of did this on purpose. Does anyone see anything that's going to happen here? When I plug a 1 in, I get 2. What do I get when I try to plug a 0 in?
It's
Undefined.
Undefined. Which makes sense, because what does this thing do at 0? This piece is going to go, whoop, it's going to go up forever. That area is going to become infinite, yes? Okay, so we'll investigate infinite areas later. Okay, so what about this guy? So this would be undefined at the moment. Yes, sir?
What's that little line here?
Oh, this here? So again, this means this expression evaluate from 0 to 1. That's just kind of the standard notation that we use for this. Yeah. Just to remind us what the hell we're supposed to be plugging in the damn thing. Yes?
So we would have put F, like when we found x cubed plus 1 over x, we would have put big F of x cubed plus 1 over x.
No, because this is big ass F of x. This is big ass F of x. So when I do plug a 1 and plug a 0, and I'm doing big S F of B minus big S F of A.
So you just still say big F equals this stuff.
If you want to, yeah. You just like saying it. So what about this guy? So here's where
Negative.
here's where I can hear the gears. Because derivative is forward. Integration is backward. And I can hear, "Ah!" What's the derivative of sine?
Cosine.
So what's the antiderivative of cosine? Sine. The derivative of cosine is negative sine.
Negative sine.
Do you guys see? Do you guys see how easy it is to get the wrong thing there? Completely understandable, and I'm still going to take points off. Because I'm equal. I'm not going to take a ton of points off, just like 20. So what is the integral of cosine? I'm sorry? Sine.
Sine.
Now what happens here? What's the interval? What's the antiderivative or the integral of negative sine?
Negative cos.
Good. And how do you check yourself? What's the derivative of cosine? Negative sine. See, derivative of cosine is negative sine. There you go. Evaluated from 0 to pi over 2. So what do you get when you plug a pi over 2 in? You get 1 plus 0 minus, so that's f of b, yes? Big S f of b. Minus, and the one big thing people forget is I gotta subtract everything. In this case, it's not gonna make a big deal because one of them is gonna be 0, but, so when you put a 0 and you get 0 plus 1. So I get 1 minus 1, I get
0.
0. Yeah, real quick, just to kind of show you guys.
That makes sense.
Doesn't cosine look like this?
Yep.
Really bad, but oh well. Doesn't sine look like this? So at here, it's its maximum. Doesn't this area kind of cancel out with this area? I mean, because one is underneath the other. I don't know how to tell you. If I take the difference between them, it would be above the x-axis and then below the x-axis. So they would actually cancel. So it makes sense that the answer is 0 here. Okay. That's surprising. I need you to understand. It is surprising that this entire process can be shortcut into finding antiderivatives and plugging shit in. That is neat as hell. I don't know if I can impress that upon you enough. That is unexpected, awesome. Dear God, thank you. Why do we want to find areas? What the hell's up with us? Why the hell we always want to find these freaking areas? Because very often in the real world, I know rates of changes of things. And then I want to calculate the amount. So I know the rate of change of carbon dioxide going into the atmosphere. I want to know the amount of carbon dioxide that goes into the atmosphere. I have to integrate the damn thing. How do we undo a rate of change? Which is an interval now. So I can integrate from this year to that year to see how much carbon dioxide has been put in the air and how much life we don't have. Okay. I feel like I'm in a doobie place. Anyway. One last thing. If I had the interval with no limits, you could do it, Jeff. Sure. the integral without limits. If the integral with numbers on it is the definite integral, this must be the indefinite integral. It has no idea. All this is the antiderivative. This is like, this is just saying, I don't know what to plug into it, just get the antiderivative. So what is the antiderivative of 3x squared?
X cubed.
Plus c. Why did the plus c disappear for definite intervals? Because f of b and f of a would both have plus c. I'm subtracting them, so I never have to put a plus c for the definite intervals. This is an indefinite. I'm not subtracting anything. There's nothing there. Not zero. There's nothing. So I just stop at the antiderivative because I don't know what to plug in there yet.
So the f of b minus f of a is the
Definite integral. Kind of makes sense. This is like getting big ass f, and then if they gave me numbers, I would know what to plug in and subtract. Yes. So this is like one step before that. I don't know what to plug in, so this is just what it is. That's enough. That's enough. I'll stop. No more. One more thing. I'm sorry. That's it.
So how would you go about that? The same thing?
What's that? That's the last. I can use some more if you want.
So
Everybody, Tyler wants me to do. Tyler wants me to do some more. No.
how do so
Get
then
out
how
of here.
do
Go
you-
ahead. Go ahead.
How do you do that?
Yes. Monday is a holiday. Yes. Not just for me. It's just generally a holiday. So don't come to any classes on Monday.
So that's just the answer for that?
Yes.
There's no subtracting or
Because again,
there's no okay.
there's not even a zero there. There's nothing there. So this is kind of like the first step would be get big ass f, and now it's just waiting for somebody to tell it what to do with it.
Okay.
Yeah.
I've got a couple questions. So,
Yes.
first of all, let's just define